Welcome everyone. In this video we will discuss second order linear homogeneous differential equations. I know those are lots of words, but don't worry, our discussion will show us that this topic is in fact quite easy to deal with. So let's say that we have a differential equation in the form, let me change there we go. So in the form ax, this is a function of x and the function is a, times the second derivative of y, so y double prime, plus bx y prime plus c of x y equaling d of x. This is the general formula for a second order differential equation, right? Because you have the second derivative of y as the highest order of the derivative. So this is a second order differential equation. What makes it linear homogeneous is though a special case of this. The special case that we need to consider is where these functions that you see, we need to consider the case where these are not functions. That makes it a homogeneous linear differential equation, a second order one, of course. So we have a y double prime plus b y prime plus cy. And I forgot to say this d of x, that's also a constant, and it is a special constant. It is 0. One of the most famous numbers of all time and one of my favorite numbers of all time. So we got this. The question that you need to ask here is, why would I care? I mean, okay, fine, but how does this help me? Why do I care? Well, it turns out that we can use this in many areas. For example, I want to consider a case from physics. I want to consider a spring mass system. And it will be an ideal spring. There won't be any frictional forces. So let me draw the system. We have a wall, a spring attached to it, and a mass attached to the spring. We have the mass of the mass, we have the mass of the mass, we have the mass of the object, and we have the spring constant as k. Now, from Hooke's law, we know that the net force acting on this object will be, so F net will be negative kx, right? And x here is the displacement from the equilibrium. So this is the equilibrium, this is x. And this is going to equal, by Newton's second law, it is going to equal mass times the acceleration. Now, we know that by the definition of acceleration, it is the second time derivative of position. So we in fact have negative kx equaling m times, instead of a, I will write the second time derivative of position. So it is x prime you could say, but the more convenient, the more conventional actually way of writing it is by putting two dots on top of x, right? This x double dot is equal to acceleration. It means the second time derivative of position. This is by definition, okay? Now you can see that if I add kx to both sides, you can see that we have mx double dot plus kx equaling 0. And this is, my friends, a second order linear differential equation which is homogeneous. This is a homogeneous differential equation. Because look at this. Mass here, so A here is the mass. B here is, well, it is 0 because the first order time derivative of x doesn't appear in the equation. So B is 0, C is k, and of course we have it equal to 0. So it turns out that this second order linear homogeneous differential equation can be encountered quite often in a physics class, right? This is a very classic system, a spring mass system, and it turns out that the motion formula for it is a second order linear homogeneous differential equation. I really like to say those words back to back. That's a good sequence. So the question becomes, how do we solve these, right? How do we solve these? Well, let's do the solution on the new page. Alright, so let me write the general case one more time for the second order linear homogeneous differential equation. We have this as the general case. Now the thing here is, we need to think carefully on what y can be. And when we think about it, we can notice that something like e to the power of lambda x might actually solve this differential equation. And how do I know it? Well, I know it because think about this. If I take the first derivative with respect to x, I will have, so by the chain rule, I have lambda and then this factor again, and if I take the derivative one more time, I will have this, right? And why did I say that this might solve it? Well, this might solve it because we have that this is equal to 0. The whole expression here is equal to 0. And when we substitute this, all of the e to the power of lambda x terms will cancel. And when they cancel, we will have a quadratic equation in terms of lambda, which we can solve using the quadratic formula, right? So let me substitute this. We have a, instead of y double prime, I will have lambda squared e to the power of lambda x plus b. So we have lambda e to the power of lambda x plus c e to the power of lambda x equaling 0. And we can divide both sides by e to the power of lambda x. Oh, can we do that? What if it is equal to 0? Well, it is never equal to 0, okay? Think about the graph of e to the power of x. It never touches the x-axis, I mean. So don't worry, it will never be equal to 0. That means we can simplify by it. And when we do that, we get the generic equation a lambda squared plus b lambda plus c equaling 0 as the quadratic equation that we need to solve to get the lambda, because when we get lambda, we will be able to substitute it here to get the function that satisfies the given differential equation. Alright, I hope this makes sense. It might be a little abstract for you, so let's just try this on the spring mass system, and then it will be much more obvious, I hope. And also, this is given a special name. This is called the auxiliary equation, right? It is kind of a equation that helps us to solve the given differential equation. Alright, enough vocabulary, and let's now move on with the spring mass system. So for the spring mass system, let me return to the page. Well, we can even, let me write it. So for the spring mass, we have mx double prime plus kx equaling 0. So if I substitute these to our expression, and this time instead of y we have x, that changes nothing. Absolutely nothing changes in our approach. We have m lambda squared e to the power of lambda x plus k e to the power of lambda x equaling 0. These guys drop. We get that m lambda squared plus k equals 0. And so we can solve for lambda squared then. Lambda squared is equal to negative k over m. Which means, interesting, lambda is equal to what? How is this possible? Lambda is equal to the square root of negative k over m. So it is equal to I times k over m. Ooh, we got an imaginary number for lambda. Is this possible? Is this allowed? Well, of course it is allowed. Why not? Why wouldn't it be allowed? And so the formula for the position for the spring mass system then would be that x is equal to e to the power of I k over m under the square root. And if you know Euler's formula, then this will be equal to, you know that it will be equal to cosine of, well, let's see, what do we put? We have cosine of, cosine of the square root of k over m times t plus I sine of the square root of k over m times t. Okay, and also notice that I should have perhaps said this at the beginning. You can have other factors here as well, right? Like you have but some constant, let's call it e. Okay, you could have them as well so that they would cancel, they would be simplified, and you can even carry it out to here, and it will be apparent here. This is called the amplitude for the spring mass system. It undergoes a simple harmonic motion, but we don't need to get into it. What is the main takeaway from this video? Well, second order linear homogeneous differential equations are helpful because they appear in physics and they are quite easy to solve them. I know the name might be scary, the second order linear homogeneous equations, differential equations, but they are quite easy to solve. It all boils down to a quadratic that we call an auxiliary equation. I hope this video was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then.